Welcome back to the lab. Welcome back to EE for everyone. Today we're going to be continuing our series talking about how to use EDA tools. This is an awesome series, and we're capturing a motor module from the motor series, which we'll be resuming right after the series is complete. So if you're into circuit design, electronics design, you're trying to learn how to use an EDA tool for yourself, there should be a little bit for everyone in this series, and I'm pretty excited. Today we're really going to zero in on schematic capture and simulation. These two really walk hand in hand, and one is all about capturing the design, and the other one is all about testing it in a theoretical environment. One core piece of this is SPICE, which is an ancient tool, but in a good way. It's really grown a lot over the years, and it's become an incredibly accurate universal language for sharing circuit models and simulations. And so you'll find a lot of different tools with a lot of different branding, but under the hood, it's usually SPICE, which is awesome because that's a common platform. If you understand SPICE, then you can use almost every circuit simulator. And if you're curious like me, and I'm not even sure if this is right, but I just had to look it up because SPICE, all caps, you're like, that's got to be an acronym for something. And the most credible explanation I could find was simulation program with integrated circuit emphasis. Maybe it's right, maybe it's wrong, I don't know, but pass the smell test for me. So anyways, let's dive in. We are in a KiCad or KiCad project. We're in version 6, and I've done absolutely the minimum amount that I can while still claiming to make a video. So I copied over the old library, put it in a 6.0 library directory, and then pulled forward the old symbols from these couple directories. Basically, I just pulled in the old library, clicked migrate, made a new one, and this way I'm pulling forward some old symbols that I had made in the previous version of the tool. With that said, we are into part 1. We're going to do 4 major parts of this video. Part 1 being simulation, and this is a really interesting simulation challenge. I was looking for a DC motor driver that should be able to handle a lot of what we would want to do, something that seems reasonably robust, at least a good enough starting point. It's rated for a 3.6 amp peak output current, and it looks like they have a reference design that's made for 1.4 amps continuous. This is a part from TI, so the datasheet's pretty good, and it talks about just the internals of the device, and this does some current regulation, which could be really handy for a system like ours that's meant to be kind of modular. This will give us a predictable maximum current for stall and high inertial load conditions where we might be pulling full current through the motor. It also has a wide operating range and a relatively low typical RDS on. So this should work really well for our first brush DC motor dev kit. And this is the component that I'm really going to focus on for our example today. So this brings us to the first challenge, which is simulation. How do we simulate a part like this? Here we are on the page that would have the symbol if it was here, or rather the simulation model if it were here. And it looks like when we come down to design and development, they only have hardware development kits. They didn't make a model. Interesting. Well, I guess that means that I'm really lucky because I didn't want to import their model anyway. And so what do you do when you want to simulate a system, but you don't have a good model? Well, I'll show you. Oh goodness, I was recording that whole time. Well, good. I'm glad that I was recording. We can time-lapse that now. What you have now is the simulation, and I have modeled the motor driver pretty simply. This is going to be driving in one direction. In this case, it would be like the forward direction, where VM plus is generally higher than VM minus, with the RDS on modeled for the motor driver and an assumed switching slew rate of vmote in 0.1 microseconds. Perhaps that's not the correct slew rate, but we can make this model better and better as we dig into the datasheet and learn more about what is going on. In the same way, we're modeling the motor as a load with a resistive element, a inductive element, and a back EMF, where the back EMF will be proportional to motor speed. Now, the motor that I'm using isn't well characterized, so if we want to look at like maximum current or maximum load, it's pretty easy to see that the EMF being 0 volts would make the resistance and inductance require the most current. But before we can do this, I need to run down to the lab and I need to get our LCR meter to measure the real inductance and resistance of the motor. Parasitic resistance of 20 ohms and an inductance of 12.2 millihenries. On the driver's side, we have a motor voltage of 12 volts, a duty cycle of 50%, and a frequency of 40 kilohertz, along with an RDS on of 565 milliohms or 0.565 ohms. That's from the datasheet. The slew rate is assumed to be 120 volts per microsecond, which is pretty fast. I don't know how fast they switch, but we'll pull that in later as we need to. I don't think that it will impact this simulation too terribly much because we're not evaluating power dissipation in the FETs. You'll notice a few things that I have done, some spice directives that I've called. I've called this parameter spice directive, which allows us to define different things. In this case, it's defining some variables that are used in the simulation, and then to call those, we put that name inside of curly braces. And if it's not curly braces, I'm about to make a fool of myself because the simulation won't run. I'm pretty sure it's curly braces. Let's go ahead and put in 2-second stop time. All right, so now we have a transient simulation command as well. Transient simulation, 2-second runtime. And hopefully, we will be able to measure with cursors that our parameters had the desired effect. We should have a signal with a frequency of 40 kilohertz and a duty cycle of 50%. Well, let's do it. We'll click on this once to get one cursor. We'll click on it again to get a second cursor. We're going to grab our first cursor and put it on a rising edge. Second cursor, put it on another rising edge. And now we should measure 40 kilohertz. Now my cursor placement isn't perfect. Let's zoom in a little more. I'm sure I can get it better. Sure enough, wasn't quite right. That's a lot closer. And yes, 40 kilohertz is the period. Now the duty cycle we can measure by pulling this cursor over here, and we should get right about 80 kilohertz, and we do, so that's 50% duty cycle. Phenomenal. We pulled in all of the parameters, and this source is behaving correctly. T on is 0.5 divided by the frequency, and the period is 1 divided by the frequency, which, of course, results in period. So this is showing just one spice directive, the parameter statement, and how to do parametric simulations like this, which is great because once you have it set up, you don't have to think too hard. You just come in here, you change your variables. So let's say you use a different motor, right? This tells you which parameters you need to use, and then it uses it in an appropriate situation. This is great because if we want to model our EMF as a function of speed, we can actually put that equation into Spice, and then you can actually put RPM as a variable, and that gets used so you can do the hard work once, set up all of your equations, and end up with a reasonable model. Speaking of, let's look at our motor current here. So we can see that at t equals 0, there is a massive spike in current. Well, nope, that's not right. There's not a massive spike in current. It's modeling current in the wrong way. Let's see if I can spin it around. Control R. Oh, right. You can see that. I'm going to place it, and hopefully the current is going the right way now. Let's run this simulation again. Hey, there we go. Motor is positive now. I'm going to attempt to stop the simulation. Yeah, I changed the plot. It's plotting all of the things that I asked it to plot, which is so great. I'm so glad it's doing that. Okay, now, okay, it finished the simulation. Great. Based on the simulation, assuming there's no EMF, we would expect this motor to have a DC current of approximately 280 milliamps. I'm actually tempted to hook this up to a 12-volt source and test it, so I'm going to do exactly that. Okay, I did the measurement on the real motor, and I got a current of 0.08 amps, which, according to our model, would lead to a voltage across the motor of only 1.6 volts, which would mean that our back EMF was 10.35 volts. Now, I don't know if that's realistic. I could have just forgotten a number or written it down wrong. I don't actually have the appropriate characteristics of this motor to know for sure if that's right or wrong. However, we'll just assume that's right for right now, and we'll use EMFs between 10.35 and 0 volts to lead to a full speed, no load RPM, or max speed at 12 volts, and stall. Let's do something here. I want to show you another element of simulation tools before we move on. So let's say for a minute we wanted to look at how duty cycle affects this simulation. I'm going to pull duty cycle out. Okay. And I'm going to add another parameter. We're going to do .step param. We're going to paste what we have. And this is not a valid command. I'm just getting the right prompt. So now LTSpice is saying, wow, you have a step command. What would you like to do? We want to step the parameter D from 0.5 to, actually, let's do 0.1 to 0.9 in increments of 0.1. This is going to run a few different simulations. Hit save. I'm going to terminate the simulation at 40 milliseconds instead of 2 seconds to reduce our sim time. Okay, let's do that again. There we go. That's a lot better. And what we can see is as we are changing the duty cycle of this motor driver, we are then changing the current through the motor. Very good. And that is real. It's not quite this extreme, right? I'm assuming that the motor is stalled. I'm assuming that someone is holding this motor. Absolutely cannot move. You're pushing against a brick wall. You never accelerate. So this would be like the maximum current at each of those set points. According to what we measured, we need to verify these measurements with some experimental stuff. Any model that's unverified will almost certainly have some glitches, whether it be an off-the-shelf SPICE model that you grabbed from a component vendor. I'd assume they did some testing to validate it, but you always have to validate a model, especially when it's one that you are creating. Right, so this is giving us some ideas about power dissipation, though it's only resistive losses, not switching losses for the motor driver. And if we hold Alt and click, it'll plot power. If we click again, it will show only that variable, and we can get an idea of some power dissipation numbers. It looks like it's only grabbing the first one, so I don't love that. But you can just look at the graph, and you can see that it's maximum of about 75 milliwatts of power dissipation in one MOSFET, so you have to double that for the part. You'll have the current flowing both in and out of the motor driver as we've modeled it. And we can also look at what voltage we could expect to see actually across the motor. Oh, goodness. Let's do that again. Okay, yes, we can see the PWM waveform across. Oh, that is pretty neat. And the voltage there, well, we'd have to do the average voltage, which I don't believe you can plot. If you do a control click, yeah, you can't integrate it. We could integrate it. You could get metrics. Well, whatever. I think you get the point. All I wanted to show is you can run a simulation. You can step parameters. That is another reason why I like doing it like this. It makes more sense when you look at something like current because you don't need to integrate it. I mean, technically you'll get some error because you need to try to get the midpoint of that wave, but you can get things like current ripple. You can get some parameters of the circuit that you might care about when building a system like this. All right, I think we have beat this dead horse dead enough. I think we can move on from simulation. Let's talk about how to actually create this component in KiCad. Here we are in KiCad. I'm going to open the symbol editor, and we're also going to grab the datasheet. We're going to need both of these. And I'm going to start by grabbing the library. Should be a library in here called Orderable IC. Excellent. You can see there's a few TI parts already in here. And the specific notation that you use doesn't really matter, but it's important to think about what you want to do. What I've been doing historically is to start with the vendor name. In this case, that's TI. You can see that I have on semiconductor, NXP, some Phoenix, ST, Micro, TI, a few different people, Microchip. I just have analog devices even. Wow, I've got a lot of different vendors represented here. That's awesome. But so this is a TI DRV 8870. So that's what we're going to call this part. A U prefix for a... There we go. All right. I'm just going to save this to put this in the library. I'm going to move a couple of these elements. There we go. And we're going to pull up the symbol properties. And there's a couple fields that I have started to do, and these are not mandatory by any means, but this is just good practice. So at a minimum, manufacturer. Some people will spell out manufacturer. I just prefer a shorter prefix. I do MFG for manufacturer. And then again, manufacturer part number, which you could spell out, but I prefer an abbreviation. I've been using manufacturer part number abbreviated like that, which is just what I have done in the past. These are all hidden. I have also been known to add like a value show parameter because it looks kind of messy to see TI DRV 8870. So I might abbreviate that and just say like DRV 8870, and I'll show that on the schematic. For the data sheet, I'll copy over a link and we'll put in Texas Instruments for the manufacturer, and we'll put in the full orderable part number, which is a little bit longer for the manufacturer part number field. Grab the description. I'll usually just grab this off DigiKey or wherever I happen to be, as well as some keywords. And now we need to look at the footprint. But before we do that, I'm just going to save to pull in all those parameters and save our work so far. All right, so grab the two visible parameters, and all the invisible ones are up there. Great. We have a couple more to do. Actually, just one, and that is the footprint. So this is where we need to consider the datasheet, and they will probably have a recommended land pattern. There's the package description. There we go. What I would probably do if I wasn't doing this as an example is I would look in here for a equivalent footprint, and that would most likely be under the package SO8 with an exposed pad. Thermal vias. Okay, what is the size here? It's got a package size is 3.9 by 4.9, so it looks like this one, and the exposed pad is what's the nominal size here? Looking at 3.3-ish by 1.8-ish. But we probably want that exposed pad sized so that it will fit everything no matter what. What did they recommend here? They recommended 2.4 by 3.1. So this is actually really close. It's not quite what they specified, but it has the right pin spacing. It has the 1.27 millimeter pin spacing. The overall dimensions are pretty similar. It has the right amount of vias. I don't know if they're the right diameter. This is close enough that it would probably work and not have too bad of solderability. If you weren't watching, I'd probably just use that and move on. I'll be honest, I'll own it. But since I'm not being lazy today, we need to go into the footprint editor, and we're going to make the recommended land pattern. We'll just put this right in our global library. So we're going to make a new footprint in here. We're going to call it TI DDA, and then it's R PD SO G8 therm via. There we go. And now we can make everything exactly how they want it. Okay, so now I need to take a look at how they made their dimensions. Where we want to start. I'm going to start by placing a pad. And we're going to do it exactly how they specified. So we want this to be a rectangular pad with a pad size in the X dimension of 0.45 millimeters, and the Y direction we want 2.15 millimeters. Great, there's our pad. And we now have one pad centered on the origin. I'm gonna come in here and edit some parameters. And specifically, I want to specify the solder paste clearance. So they're specifying a 0.45 millimeter, which is how much smaller than the pad? So it looks like, okay, so for this solder mask clearance, they want 0.07 millimeters, and the paste clearance is going to be 0. Oh man, I gotta divide by 2. 0.5 minus 0.45 divided by 2. There we go. I wanted to make sure I didn't get off by a power of something crazy. Okay, we're looking pretty good with the clearances that I have put in. Hopefully this works. I'm gonna click OK. And now if I go to the paste, front paste, is that bigger? No, it's smaller. Great. The paste looks perfect. It's exactly as specified by, and I'll add a comment in here in the front fab, maybe user drawings. Now this is where I don't usually use these layers. I'll put it in user comments because I don't use that for anything else. And I will say stencil solder paste made for 0.127 millimeter thick stencil. Solder paste for 0.127 millimeter thick stencil. There we go. There we go. So that's just on a comments layer. That's a good reminder for future me. If you're making a stencil, this is what the clearances were made for, according to the datasheet. If I want to do something else, I'll have to reevaluate. So let's just double check what we did here. I totally goofed that up, didn't I? I grabbed the solder stencil size. 0.5 is the size of the pad. Wow. Pad geometry, note C. So now we have a 0.5 millimeter by 2.2 millimeter pad at a 0 degree angle. That looks correct. That is pad 1. Okay. So now we need to start doing the spacing. So this is where it gets fun. I'm going to do Control T, which is create array. Horizontal count will be 4. Vertical count will be 2. Horizontal spacing is our pin pitch, which we can see defined right here as 0.127. Sorry, 1.27. They're using European notation with commas. No, yes, with commas. And vertical spacing is given here as 5.75 millimeters. Though I believe we will need to do negative because of the way I'm drawing this. Pin 1, as shown here, is bottom left. We want to go 1, 2, 3, 4, wrap around, 5, 6, 7, 8. Continuous, starting from the start value, which is 1. And we want to reverse numbering on alternate rows, columns. I believe that is correct. Let's click go, and what do we get? Yes, 1, 2, 3, 4, 5, 6, 7, 8. That is what we get. I'll just undo this for a second to demonstrate. I'll do Control T again. That'll pull up our settings. And if I don't check reverse numbering, you notice we get 1, 2, 3, 4, 5, 6, 7, 8. No, that's the wrong pin numbering. Sorry, not edit. Control T again. Gonna check that box. Another thing that you might make a mistake on is if you don't hit negative. Now you have 1, 2, 3, 4, 5, 6, 7, 8 wraps around correctly, but your pads are on the wrong side, so that is not correct. So we're gonna not make a mistake. We're going to do it correctly, and now we need to add in the thermal pad. So that's great. That just put in most of the hard work of getting your pin spacing correct and numbering it and placing it all. That's great. That's part of why I love symbol creation in KiCad. I love that create pad array. I would hope every tool has it, but in my experience, they haven't all had that. All right, so we need to make one more pad. And I'm going to start with this. Let's see, we have a different pad here. We're going to call it pad 9 for the exposed pad. Some would allow you to do EP for exposed pad. I'm not sure if KiCad allows for letters in the pad number field, so I'm just going to play it safe and use pad number 9. And they give a width of, they recommend 2.4. They recommend 2.4 millimeters for the height and 3.1 millimeters for the width. For solder mask, I believe that is correct clearance. For the stencil, they're recommending that we use 3.1 millimeters and 2.4, which is the exact same size as the pad. So we want to set our clearance to 0 for this part. Okay, with the paste clearance set to 0, I think we're all set, though it does want solder mask. Yeah, that should be fine. Solder mask. Oh, wait, they want a solder mask defined pad there. I totally goofed that. Okay, so they want 2.95 and a 4.9. Okay. But I don't think I can do that. It doesn't allow for... So we can do a 2.95 divided by 2, 0.275, 0.275 clearance. But then I need Sorry. That was totally not right. Got a negative 0.25. And it's the 2.95 times 2 plus 3.1, 3.65. So that will give us as close as we can get to their pad shape. So this will have the copper extending to the extent that they specified, with the solder mask defining the pad down to... Interesting. This is the first part that I've made the footprint for that has a solder mask defined pad for one and a copper defined pad for the other. But I mean, yeah, it's fine. So if we just double check that with the front mask, sure enough, we have the solder mask defined pad. I'll just double check the dimensions there. Should be just more than 3, and it is. Should be 3.1. And the other direction, we've got just about 2.5. Should be 2.4. So yeah, that's pretty close. I could change the grid, but I don't want to, so I will not. Quite good. Now we just need to put in our thermal vias. Should be easy enough. We're going to place down a new pad. We're also going to call this one pad 9. Not all tools allow for pads which have the same number. We're going to call this a circular pad with a hole size of 0.33 millimeter hole. And we want the pad size to be, well, let's just make it something reasonable, like 1 millimeter. What's the closest we are to the edge? 1.3. 1.3. So we're 0.82 millimeters from the center. So I will do 0.6, which should give us enough room to not extend outside of the other pad. All right, cool. All right, now this is going to be tricky because we need to center that on the center of the pad. And we're going to need to do some math to get that right. I'll just place it approximately where it needs to go. So keeping in mind that this is currently 0, 0, we need to get 6 of these holes. So in the center of the part, that'll be 1.27 plus 1.27 divided by 2 to get to the center of the part. So it'll be 1.905 millimeters. Position X. And then we need to subtract 1 hole spacing. So we'll take off 1.3. That should leave us with 0.605 in the X direction. And in the Y direction, okay, so we want to go to the center of the part. So we will take 5.75 divided by 2. That should get us to the center line from the center of the pad. So I'm going from here to here. That's what I'm hoping to do. That's 2.875 millimeters. Then we want to take off half of that 1.3. So we'll subtract 1.3 divided by 2, leaving us with negative 2.22. 2.22 millimeters. See how that looks. So they want that first hole to be pretty much exactly lined up. Yeah, it seems about right. That hole should be just barely off of that solder mask defined area. Yeah, it looks about right. Maybe I'm off by just a smidge. I don't know. It's hard to tell. Well, let's make our grid, and let's use that as our confirmation. So we do a Control T. Horizontal count 3, vertical count 2. Horizontal spacing is 1.3. Vertical spacing is negative 1.3. And we want to not number at all. I don't think that's an option. Yeah, that was not right. Okay, I screwed up the math. Oh, the pad's not centered. We need to center this pad. I think I did get that correct, but this pad's at the wrong location. Okay, so to get the y coordinate correct, we need that 5.75 divided by 2, which is 2.87 millimeters. And then we need to get this centered in the other direction, so we will take 1.27 plus 1. We can just multiply by 1.5. 1.905. That'll probably look a lot better now. Yeah, look at that. If we check the front mask, there we go. That's nice and centered in both directions. That's great. Now let's see if we can really go for gold here. So we want to grab a 3D model. Package so.3D shapes. And now in here we want 3.9 by 4.9. That looks right. I'm going to rotate it. Offset. This will be the same two numbers we've been doing. X will be 1.905. Y will be 2.875. Oh, look at that 3D model. That looks awesome. Click OK. Hit save. And now we have a 3D model. We didn't make a new 3D model, but at least it has a 3D model. Whew, we are getting close. Oh, that is awesome. Quite good. So we have the thermal pad that is solder mask defined. We have the vias placed as specified, the right drill size, and they don't overlap the copper area. It looks fantastic. We have the copper defined pads on the outside as specified that are the correct size and pin spacing. Everything looks great. Pin numbering is correct. So now there's only two more things we need to do. We need to put our courtyard in. So this will be a placement keep out around the part. I need a grid that is lined up better with our design. Okay. Dunk, 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 dunk. That looks more even. I like that. And then we want a couple solder mask features just to assist in placement. Okay, so this is where I'll switch from this drawing back up to the package drawing. We want to capture that maximum size. How did I not? There we go. So that is center-ish of the part. 2 point. Yeah, I can't quite get there. That's as close as we can get to the center. And we want to go, what's 1.27 times 3? 1.27 times 3 It's 3.81. I'm not zeroing. What in the world? 3.81. Okay. Here I am, zeroed out. There we go. So I'm looking at my guides, and yeah, it just wasn't right at all. Okay. So 2.5. Right on. I'm just going to sketch in this line for now. And I'm going to set my start point to, okay, we want to capture that 4 millimeter size. 4 millimeters. I need to look at all the math that we've done. So we're on center of a 2.2 millimeters. That's 1.1 millimeters. Now let's just go right to the center, which will be 5.75 divided by 2. Okay. That gives us a starting point. And then if we are 4 millimeters in total, we want to subtract 2. Then it'll give us a value of 0.875 that we want for Y1. And we want a negative 4.875. And just to be exactly correct, we want that 1.27 times 1.5 minus 2.5, and that'll be a negative 0.595 millimeters. There we go. Oh, really? Is their footprint? Do they show this on the pads? Well, whatever. So there it is. And to designate pin 1, I'll just go with the standard notation for KiCad libraries, which that might be too close. I might need to bump that out a little more. 0.595. That's where we want to start. That looks pretty good. Okay, we have the pad defined. Gonna need to expand that keep out area just a touch. There we go. Pin 1 indicator. Done. Silk screen. Done. Just look at the 3D preview. That is looking good. Why don't we place that reference just for good measure? And let's compare that here. Look at the 3D preview. Ooh, actually, that's a good point. I should be using the environment variable. I will do that. They did the same thing. You got the wraparound on the bottom and the top with the little arm thingy. And yeah, that looks about right. Oh, and it actually substituted that for us. Wow. KiCad's on its game. This looks excellent. All right, we're done. We've made the footprint. Holy cow. This is going to be the longest video ever. Okay. There are a couple different schools of thought when it comes to organizing symbols and pins. So I'm going to start with an unpopular choice, which is just physically matching the IC. And to do that, I will start with pin name, ground, pin number 1. This is a, I prefer to call grounds passive pins, personally. That's what I like to do. Just because it'll throw an error if a power input is not driven. And that is a little bit annoying. Period. That's all I gotta say. Enough said. Okay, and this is my favorite shortcut, so pay attention. Insert gives you another pin spaced exactly correctly underneath it that copies everything and auto numbers where that makes sense. If you hit E, this is why I love doing this in KiCad. It has so many shortcuts. I've seen tools where this is like click, 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 click. I hate clicking. I have tendinitis. Clicking sucks. Keyboard shortcuts are a lot easier on my wrists. So, anyways, pin name for pin number 2 is in2. This is pin 2. I'll hit enter, insert. Now you have pin 3 that's called in3. It assumes you want to go up. Well, we didn't really. We wanted to go down. This should be in1, which is pin 3. Beautiful. Now hit insert again. You end up with your 4th pin. They called it in2. We're going to call this Vref. Going to hit insert again. That'll give us pin 5. We're going to call this VM. Insert again. We're going to call this out 1. It's pin 6. Now this is going to be ISEN. It's pin 7. Insert again. It's going to be out 2, which is a, going to call, we're going to call this a power output. We're also going to call out 1 a power output. I sense. Okay, they call this a power as well. I don't think that's quite right. Yes, I'm going to call this an input. I might call that one passive. I just don't want design rule issues coming on that pin. VM is a power input. That's your motor power. Vref that is an input. In1 and in2 are also inputs. Beautiful. So we have our pins. What I want to do is I want to grab these, then you can mirror them left and right, and then mirror them again for vertical. And that's all there is to it. Yeah, it's beautiful. That worked a treat. That's what, 3.6.35. We'll do that again. There, that's centered. And now if we wanted to just finish this, right, I could wrap this around, take it to there, and then fill with body outline. Oh, no, no. There we go, fill with background color. And that kind of looks like an IC, right? And so here's what I like about this configuration. What I like about this configuration is you can lay out your schematic and think about the physical implementation. Like if you pile a bunch of parts on this sense pin or a giant part, you have to remember that that's going to be in your way when you're laying out one and out two. That's going to be a problem. Likewise, a bunch of big capacitors on VM, you can think about, okay, well, maybe we'll put them off over here, over there. And I like thinking about the system while it's being configured. Oh, I understand now. iSense is actually power. Okay, so we're going to call that power output. Ooh, but that's going to cause problems. No, it won't, because it's got a series resist. Ooh, but it'll cause problems if we short it to ground. Ah! I think I'm just going to call it passive. I hate false errors in a DRC report. Okay, that's good enough. It's not perfect. So that's one way to lay out the symbol. Another way to do it is to group things, right? So you can put all of your inputs on the left, all of your outputs on the right, with ground at the bottom right and power at the top left. That is a common way to group your symbols. It doesn't match the real behavior of the part anymore, but you're thinking about how you'll use it in the schematic. So it's like the exact same thing, just different. Right? So in the schematic, you might want to short iSense to ground. You will have a resistor between them or a short. That's how it works. So you place them next to each other to make your schematic capture a little easier. You have out 1 and out 2 that map to in 1 and in 2. So you'll probably want to configure them in a way that makes more sense in schematic land. So 1 goes to 1, 2 goes to 2, and it kind of goes right across. That is another way to think about it. And in fact, if I were to do this, I would probably put Vref up there, because it's kind of like a power input as well. I don't know if one's really better or worse than the other. What I think is more important is that you're consistent. Whatever you like to do, just do that. Don't bounce back and forth, because that's when it gets really confusing. Just stick to whatever makes sense to you. Do that on all of your symbols, and then you'll have a library that is consistent. I'm going to ignore my own advice and use it like this, even though most of my parts are laid out the other way. Cool. Okay. We have made a schematic symbol. We have made a footprint. We've linked the footprint to a... we've linked the footprint to everything we need it to. We have a link to the datasheet. Holy cow, this is looking good. All we have to do now is close this, close this. It is time to actually capture the schematic. I'm in the US, so I'm going to use US letter size. 11 by 17 is a little more common, but this schematic isn't going to be too big. This is... there we go. We have a DC brush motor. And ignoring all of the other dependencies and other things that we'll need to figure out, let's grab our schematic symbol. So we're going to search for TI. We don't want the DAC. We want this motor driver. Beautiful. And now we can see that part has been imported. We're probably going to want some capacitors. Oh, come on. I didn't import that library. Okay, 1 second. VM. Ooh, right. This goes up to 50 volts. We'll have to be cognizant of that when we pick our capacitors. I actually don't know if we have any... We have a 12, 10, 100 volt cap. Oh, goodness. Okay, I don't actually have a good cap in here for this. So I'm going to use these. I generally like to keep 30% margin on voltage rating. So that would be a maximum of 35 volts for the motor driver. which is less than it's rated for. I guess we could do that. So it wants a, what was it asking for again? 0.1? We can use 0.1 decoupling. It's got an 0603.1 mic, 50 volt cap. I'll add the label, 35 volt VM max, cap voltage limit. Excellent. And for those that aren't familiar, ceramic caps have a derating curve based on applied voltage. So that's why I'm being such a stickler. I could put 50 volts across a ceramic cap and it wouldn't cause any dangerous situation. It would just be useless because you'd be getting like a quarter or a fifth, or actually, honestly, I think you get like 10% of the rated value. If my editor's feeling gracious, I might throw up a curve for ceramic capacitor derating for an X5R cap. I think Fichet has some good graphs. But I'm going to grab a power symbol. We're just going to use the normal ground one. And I don't like putting junctions on top of pins. It just bothers me. That's why I space that down. I also avoid four-way net connections where I can. The curmudgeons trained me well. And I really don't know what I want to call this symbol. It's a V drive that looks pretty good. V drive. I think I'll go for V bus. I like that. Go for V bus. What is going on? All right. And so I'm using some shortcuts here for the wire. This node is now called VBus because of that power symbol. That's fine and good. I need to check the minimum input voltage for in1. We'll see if we can get away with that. 3.3 volt ref. We'll use that same 0.1 microfarad capacitor. This is really kind of nasty with those other caps there. We might just need to take up a bunch of vertical space. Control D for duplicate. And this is where having that library is really handy. You're noticing that I'm able to reuse some of my past work because I was organized and I captured my symbols in a way that made it easy to find what I was looking for when I came back to make my next design. There's an art to this and a bit of a science, but it's really about consistency more than anything else. Organizing things in libraries. And the nice thing about doing it like this is if I click in here, you can see well, I don't have a datasheet link for this. I guess it's a cap, but I have a manufacturer and a manufacturer part number that in theory, when you're not in a chip shortage, is an orderable part, which will make our BOM export really clean. And since I was consistent in my naming notation, you'll get a very nice BOM, which I'll show you in a second. Now, I might need to change that down the road for this Vref. That doesn't really matter. And in fact, I should probably add a series element here. I might want to put a ferrite bead. Not totally sure, but we're going to want that to have a pretty small ripple, and it was probably going to be a switch mode power supply upstream. We haven't designed that yet, right? We're starting with the motor driver, but so let's grab some small value, something not too crazy. Let's go for a 10 ohm. I still want it to be the right voltage. I just don't want ripple to get through. So you put a bunch of capacitance close to the IC, you add a series impedance, and that does you all right. Could be a ferrite bead, that might work better, but since I know the load, right, this load is a microamp or two, according to the datasheet, I'm not too worried about that. I'm not really going to touch on hierarchical design too much. I could, but I won't. That's just going to take too long. I'll just say, if you want to add another schematic sheet, you just place that down, plunk, you get a second schematic sheet, you go in and out. You can place these pins, which go out to the world. And they give you a label on that other sheet. It's phenomenal. We don't need that right now because I have been going for a long time. This video is going to be like an hour at this rate. So we need to finish it. So you place off a couple lines. And if I wanted to be a real stickler, I might add a small series impedance. But since this IC and our... Ooh. Okay, I'm actually going to add a series resistor. The reason why is because... Oh, wait, no, I'm not. Sorry, I'm at war with myself. You're watching the design process in real time. Okay, here was my thought. My thought was, I would like to have a series resistor in case there's an internal fault in this IC, and then we're left with some kind of a fault that shorts VM to either Vref or in1 or in2. If that were to ever happen, that would be pretty awful. That could be a pretty big issue, actually. Could catastrophically destroy all of the circuitry on this board. No repair possible. So I was like, great, we'll add a series resistor. That will at least limit the fault current coming through this IC back to the other domain. Cool. There's only one problem with that. When you look at the block diagram for this component, I just saw this as we were scrolling through. Where is it? See these little pull-down resistors? We're going to make a voltage divider. Pull down, typical is 100 kilo ohms. Oh, no min and max? Come on, guys, you're killing me. Yeah, so since I can't do a worst case, I mean, we could do like a factor of 10 or something, or a huge margin of safety. We're just going to need to accept that if there's a fault, well, I'll just put a comment in the schematic for me to deal with later. If internal short possible to connect VM directly to in1, in2. Mote out minus. Very good. Ground is ground. Sense resistor. The power dissipated by the sense resistor. Peak current is 3 amp. Motor current is 1.2. What is the maximum current of this thing again? 3.6. So yeah, 2.2 amp trip current seems reasonable. Man, they already did the math for me. Oh, for a 3.3 volt Vref, I trip of 2.2 amps. They say use a 0.15 ohm or 150 milliohm resistor. And did they even tell me how much power it'll dissipate? No, they did not. But that's easy enough to calculate. It's just I squared R. So that'll be 2 amps squared times R, 0.15, so that's 0.6 watts. So we need something that has at least half a watt current rating. Now let's see how lucky we are. Orderable resistors. We have a... No, I thought we had 100 milli. We have a 100 milli. Okay, so what would that give us? There'd be a 3 amp current limit. I don't love that. For the sake of time, I am going to do something a little bit crusty. I need to actually pick a reasonable current limit based on the thermal design of the board and the real motor we want to use, the real stall current involved. This is going to be a value that this is not going to be a constant. This is going to be something we need to actually calculate. And therefore, I don't feel bad at all about doing this, because if I gave you a real number, we'd just need to throw it away. I'm going to make my 150 milliohm resistor. I think you can see where this is going. There we go. Get these in parallel. Oh, look at that. And then we'll drop off our second ground reference. I'm guessing that some kind of filtering might make sense. Putting a cap off of I send to ground will probably help it to work just a little bit better, take some noise out, but that's a pretty low impedance shunt, so yeah, we'll see. So this would be a 2 amp current limit. Right on. So that is our schematic. We have it complete. Excellent. So now there's a couple things that I'm going to show you. I'm going to show you the DRC, the BOM export, and then we are done. Go to the BOM exporter, CSV group by value. I'll just click generate, got to annotate, and success, close, and we'll just import these into the PCB. What? No net found for U1. Oh, pin 9. Oh, we forgot the exposed pad. We forgot the exposed pad. Okay, one more pin. We need pin 9. This is EP. Put that right in the middle. That is our exposed pad. Nope, that is upside down. There we go. And there should be a replace, update from library, update selected symbol, close. There we go. We have the exposed pad. Now we can tie that to ground. All right, and if I pull that in again, there we go. We have the net for that center pad. Whew! All right, we have this. We can see the 3D preview. Looks beautiful. Pin 1 indicators all around, silk screen surrounds. Phenomenal. Pulled in those parts. If we run the DRC here, we'll get some errors about 1-pin nets. Power input pin is not driven by any power output pin. That's the ground thing. And 3.3 volts is not driven by any power pin. Makes sense. They don't go anywhere. I'm surprised the single pin net didn't give us any issues. That's bizarre. I would have expected some errors from these 1-pin nets. That's probably a setting. So here we can see the collated and the individual components, and we can see them grouped in an appropriate way, right? You can see the library part, the footprint, that doesn't really matter. You can see the data sheet for the parts that have data sheets. You can see the manufacturer and manufacturer part number coming out very cleanly. So we could grab this BOM, drop it straight into DigiKey or Mauser, and actually try to buy based off of these parts. Of course, they'd probably all be out of stock right now because chip shortage, but at least we could try. Oh, man. That's awesome. So, or sad, whatever you want to call it. So, yeah, we have the part. It's all placed. It's all good. We got the BOM. We've got the schematic. Whew! If that wasn't a crash course in schematic capture and simulation and, oh my goodness, just in general, EDA, I don't know what is. So why don't y'all try to duplicate this at home? I'd say I'd give you the files, but then you could cheat. So why don't you try to duplicate what we did here? And if you did duplicate this and it all looks right, Well, I can say with confidence you can probably capture just about anything in the schematic, because making your own components and pulling all of those numbers and pieces of information out of the data sheet, like that is where the real work is. I really enjoyed this today. I really enjoyed walking through simulations and schematic capture. It's such a core part of EDA tools. It just, you can't ignore it. It's awesome. It's not too complicated, and there's a lot of little details here and style points that you can make sure that you cover, little things that you can do to make sure that you're communicating clearly in a schematic rather than just communicating. But hopefully this will get you off to a good start with regards to your schematic style, when to do simulation, how to simulate, and some nuances that you'll probably run into or difficulties that you might encounter while running a simulation. I want to give a special thank you to any of you who have supported us directly via Patreon or becoming a YouTube channel member. Thank you. That really helps us a lot. And also a thank you to anyone who's interacted with our content in any way, whether that just be watching, liking, sharing with others, being subscribed, getting those notifications, whatever it is that you do to support or engage with the EE for Everyone community. Thank you. This wouldn't have anything going on without you here. So thank you very much for being a part of it. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EE for Everyone, and thank you for staying till the end. Bye.